M1, M2, and this current source having a current of 1 milliampere is forming the current mirror. So this M3 along with M2 will form a CS amplifier with M2 as the active load, and we have the CG amplifier comprising of a transistor M5 and M4. So this M4 is the load for the CG amplifier. So we are assuming current of 1 milliampere in the as I reference. So we want to have 0.5 milliampere for the CS amplifier and 1.2 milliamperes for the CG amplifier. So let us see, since we want to have 0.5 milliamperes onto the CS amplifier and 1.2 milliamperes onto the CG amplifier, the corresponding dimensions of the transistor M2 and M4 for the CS amplifier and the CG amplifier happens to be 125 and 300 as a W by L of 2 and 4. That is, this M2 will have half of this 250, that is 125 is the W by L ratio, and this M4 should have to have a 1.2 milliampere. The W by L ratio of M4 is 300. So that is regarding the M2 and M4 dimensions. So since we are having a CS amplifier for a gain of 250, so this is our CS amplifier for a gain of 250. We know that the for CS amplifier for an active load, the gain expression is given by minus GM3. This is the transistor which is responsible for the transconductance, and the load impedance is R03 in parallel with R02. Since we assume the value of lambda to be 0.01 and the current flowing through the CS amplifier is 0.5 milliamperes, R03 and R02 can be estimated and found out to be 200 kilo ohms using the equation 1 over ID2 into lambda. It is 200 kilo ohms. So this R03 in parallel with R02, which is 200k in parallel with 200k, becomes 100k. So we can actually find out the GM3, that is the transconductance required to have a gain of for a gain of 250 for this CS amplifier. So which is the magnitude of the CS amplifier gain, which is nothing but GM into R03 in parallel with R02. We can actually find out the required value of the transconductance. So GM3 happens to be 2.5 millisiemens or milliohm inverse. So we can equate this GM3 to the equation, that is root of 2ID3 mu and Cox into W by L of 3. So from this expression, we know everything in this expression except W by L of 3. So we can estimate W by L of 3 as 31.25. So if we have a transistor, this M3 of 31.25 as a W by L ratio, and this is 125, and this is our reference transistor 250, it guarantees a current of 0.5 milliamperes and a gain of 250. To bias this M3, we are supposed to have a VGS for M3, which is given by VGS is equal to VTO plus under root of the current flowing through M3 divided by cos 2ID3 divided by mu and Cox into W by L 3. So solving this by substituting the equation, the values of ID3, W by L of 3, we get VGS to be 0.8 volt. So this is a 0.8 volt and 31.25 as W by L ratio, and this has 125, and here it is 350. We're going to have a current of 0.5 milliampere flowing here, and the expected gain of the CS amplifier is 250. Now similarly, we have to find the dimensions of this M5 to have a gain of okay, let us find out what is the CG amplifier gain. Now we have a CG amplifier gain expression, which is GM3 multiplied by R05 in parallel with R04, as we can see in the circuit diagram. So this is M5, which is responsible for the transconductance, and the resistance Rout is given by the parallel combination of R04 and R05. So that's what is the expression for the gain of a CG amplifier, which is given over here. Since ID4, the current through the CG amplifier is assumed as 1.2 milliamperes, the R04, which is equal to R05, will be given by 1 over ID4 into lambda, happens to be 83.3 kilo ohms. So assuming gain of voltage gain of CG amplifier to be 400 volt per volt, So by substituting this onto the equation of gain, so we can find the value of GM5 as 9.6 milliohm inverse. So knowing the value of transconductance and ID and mu and Cox, we can actually estimate the value of WL of the fifth transistor, so which comes out to be 192. So to have a current of 1.2 milliamperes, so the VGS5 should have a voltage of 0.65, meaning this bias voltage is 0.65, here it is 0.8, the damage from this is 192, the damage from this is 300. So that's what we found here. So now ultimately we are supposed to have a current mirror with dimension as 250 W/L. The W/L of M2 is 125, which guarantees a current of 0.5 milliamperes, and M3 dimension is found out to be 31.25 to have a gain of 250, and M4 is having a ratio of W/L of 300, and M5, this 300 will guarantee a current of 1.2 milliamperes. This W/L of 5 guarantees a gain of 400. So we shall actually do the circuit diagram using Ltspice and adjust these dimensions with the bias voltage as 0.8 and this bias voltage as 0.65, and we'll verify the gain of this as 250 and V02, that is CG amplifier gain as 400. So let us do the simulation using Ltspice. So let me take the Ltspice circuit diagram. So we want to have a PMOS transistor. So let me have PMOS transistor here. So let me rotate, flip this. Okay, this is the PMOS transistor. So let me have this as a load transistor. Let me have one more load transistor, and let me have two NMOS transistor for the CS and CG amplifiers. So this is for CS. Let me write this as for CG amplifier. So giving the same dimensions, same name for the MOSFETs as in the design. So let me write it as this is M1, M2. So let me just go back to circuit and then modify. Let me make this as M3. So this is M3. This is named as M3, and let me name this as M4. And this is as per our design, paper design. Let me do the connection. So let me short all this. Okay, I'm supposed to have the source at the top. So now actually this is the source. So I have to rotate this MOSFET. So for rotating, let me select this MOSFET and Control E, and let me do Control E. Now this is fine. This also should be rotated simultaneously. Let me make this Control R and Control E. Now this is also fine. Let me do the same thing for this. Let me Control R twice and Control E. Now this is also fine. Now this ensures that the source is there connected to the VDD, and let me do this connection. So this is our VDD. So let me have this over here, and so have this, the connections done. Let me slightly move this MOSFET so that it comes in line with this. Now let me have this connection of drain to source, this drain to source, and let us short this and this. Now let me make this bias voltage to this MOSFET also. Let me connect this bulb to source, this bulb also connected to the source. Let me connect this bulb also to the source, and let me connect that current source. So to have the current source, let me go to this source and select a current source, and let me put it down here. So this connection is done, and let us connect all these two. This is grounded. This is also grounded, and let us connect the bulk of this to ground. Let us connect the bulk of this also to ground, and we are done with the necessary connections. So let me apply this as a AC source. So this is none the required voltage over here, DC voltage 0.8. So let us apply AC signal 1, which is fine here. So here it's only the DC signal you're supposed to apply. So here the DC voltage is 0.65, and this current source is of 1 milliampere. This is also fine, and we need to have a source over here. So let me select, let me copy this source. This is for copying, so I will copy this. Okay, I'll copy this source and then put it over here. Now this is should have only the AC value. Now this is having AC amplitude of 1. So let us adjust this dimension as 1U, and this is 250U. And likewise we adjust the dimension of all the MOSFETs M2, M3, M4, M5, and then come back and see the design. Okay, here I have now edited the values of dimensions of the MOSFET. So M1 is having a length of 1 micrometer, the width is 250 micron. So M2 is 1 micron length and 125 width. Now you can see the width of M2 is half of M1, so that we have 0.5 milliamperes going through the M2 MOSFET, and this CS amplifier has got an ID of 0.5 milliamperes. So looking at M4, so the W-L ratio is 300, which will allow a current of 1.2 milliamperes, and the DC voltage of CS amplifier is calculated to be 800 millivolt, that is given here, and the CG amplifier is 650 millivolt, it is being edited here. So let us do .op. Of course, the NMOS and PMOS model files have been defined here with Kp of NMOS as 200 microammeter per volt square. So this is VTO, which is 0.4. So lambda is 0.01. So similarly for PMOS, Kp is 100U, VTO is minus 0.4, and lambda is 0.01. So let me do the first operating point conditions. So let us have a look at the currents in M2. The ID2 happens to be ID of M2. This is ID of M2. Now we can say it is 0.5 milliampere. The ID of M4 is, this is ID of M4, which happens to be 1.2 milliamperes. So meaning that we are getting the required current flowing through this. So let us do the AC analysis and try to find out what is the gain of the amplifier. So let us do the AC analysis. This is decade. Let this be 100, and start frequency. Let us start from 1 Hertz to 1 gigahertz. So as we have not specified the overlap capacitances, so we're going to have a straight line. So with a gain of 250 here, with a gain of 400 here. So let me run this now. Now analysis, there is a syntax error. Let me find out what is the problem here. Now I shall do the AC analysis and try to find out what is the gain of the amplifier. So now the frequency is varied from 10 Hertz to 1 gigahertz. So let us find the frequency response. Since we have not edited any of the capacitors, it will be a straight line. So now we shall see, okay, this is the gain corresponding to this. Now we can see it is 48 dB, that is at a CG amplifier. So at the CS amplifier the gain is 52 dBs. So let us try to find out what is the gain corresponding to CG amplifier, which is 40. Sorry, I think this is 48 dB corresponds to CS amplifier. This 52 dB corresponds to CG amplifier. 52 dB of gain corresponds to a gain of 402 volt per volt, and 48 dB gain of CS amplifier corresponds to 251. So we actually expected a gain of 250